All right, welcome everyone to today's math class. In this week, we'll talk about two topics that seem different but are actually pretty closely related behind the scenes. First, we'll discuss L'Hopital's rule as a method of using differentiation to more easily find limits. And then we'll talk about Taylor series and Taylor polynomials as a way to approximate functions to some given degree, some given accuracy in a way. So let's start with Taylor. Many of you know that one already, but as a quick recap, the basic idea is this. You have a limit of that form. So you have a fraction, a numerator, and a denominator, f and g. And both f and g happen to go to 0 as x tends to whatever you want it to, right? X star. To compute that limit, one possible idea is to use approximation. So basically what we can try is we can use that formula for the differentiation, for the derivative of a function, and if f and g are both differentiable, then basically we can express them in this way, or as an alternative we can say f of x is about equal to this. So the function value at the point x star plus f prime at x star times x minus x star. Basically this is the equation for the tangent at f at the point x star, right? So we're replacing the function by the tangent, and the idea is if we're close to x star, then that approximation should be pretty accurate, right? At x star, the lines coincide, and close to x star, they should at least be close. Not exactly, but close. So basically, the idea that led to L'Hopital's rule is to say, well, of course, if g is not equal to 0, then we can express that by the approximations, and this term just cancels out. So we're left with this. Right? So if we're close enough to x star, then this is probably a good approximation. And specifically, of course, in the limit, we are getting close to x star, arbitrarily close. So it makes sense to conjecture this behavior here. So the limit here is equal to the limit of the fraction of the derivatives. Of course, this is anything but a rigorous proof, but it gives you an idea of where that comes from. So basically, it's the idea of replacing the function by their tangents, and then you'll get this law that's known as L'Hopital's rule. All right, I'm not going to present the proof, but rest assured it can be proven rigorously. All you need to remember is how to apply that rule. Basically what it says is you have, as usual with differentials, you have two functions that are defined on some open interval I and are differentiable on I. G prime is not equal to 0 in that interval. And of course you can restrict that interval to be close enough to the point that you're interested in. And you have a point x star in that interval where you're interested in this limit here. So the limit as x tends to x star of f over g. And now what L'Hopital's rule says is, well, you can replace this by this fraction here, where you have f prime instead of f and g prime instead of g. So just differentiate the numerator and the denominator separately. And you can do that under two conditions. First, those two limits are either both 0 or both plus or minus infinity. Right? That says it's equal, but I mean plus and minus infinity are interchangeable because you can always factor out a minus. Right? So either both 0 or both plus minus infinity. Of course, the functions need to be differentiable, and that limit needs to exist. So the rule only works if the limit, this new limit here, that actually exists. And remember, that also means it can't be plus or minus infinity, right? So if you get infinity here, that doesn't mean necessarily that this is infinity. That could be something totally different. only works if this limit actually exists and has a finite value. And of course, that statement can also be used for one-sided limits. So that's L'Hopital's rule. Here's a couple of examples. Well, that's an easy one that you can probably do without L'Hopital's rule as well. If you look at this, x tends to 0, you'll find that, of course, this here tends to 0, this here tends to 1, so the numerator tends to 0. This expression tends to 1, so the denominator also tends to 0. Right? So we have that 0 divided by 0 situation. Both expressions are polynomials, so they are clearly differentiable in whatever interval you want. And what we can then do is we can compute the derivative. This is what we get for f, and this is what we get for g. And then again, we can try to compute the limit. Again, try and substitute 0 for x. What we get is here, this tends to 1. This tends to 0, so the numerator tends to 1. And for the denominator, well, we've cancelled out this expression here, right? And also here, of course. So that we're only left with an n in the denominator. And that means this whole thing tends to 1 over n. Right? So that's one possible application. And then, of course, in the end, you should mention that this limit, the new limit, actually existed. So that means the application of L'Hopital's rule was actually justified. If I'm asking for a justification in questions like this, please don't forget to mention that. Yeah, something like the new limit exists, so the application is justified. And of course, you'll only know this after you try, usually. Yeah, so for L'Hopital's rule, give it a try, see if the new limit exists. If it does, all is good. If it doesn't, start from scratch. All right, here's another example. Basically, the important thing about this is the outcome here. So what we have is x to the n, a polynomial, basically. And 1 plus something to the x. So that's an exponential function. Right? So basically, the idea here is to have a polynomial versus an exponential function. And as x goes to infinity, the question is which of these grows faster? Right? Both obviously go to infinity. And through L'Hopital's rule, we can get this new expression, differentiate this expression once, differentiate that expression once. You remember we talked about that differentiation rule last week. And again, you're in the same situation. Both go to infinity. And again, you can try to apply L'Hopital's rule. So you just repeat that, and you're again in the same situation. And you do the same over and over and over again. You can see this expression in the numerator is becoming simpler and simpler, right? This power here is decreasing. So at some point we'll have a constant here. We just have to apply that often enough. That's what we do. So we apply the rule over and over again until we end up with a constant, and that is going to be n factorial. And in the denominator, well, this here reproduces basically, and this just stays as it is. So we get an expression like that. And now you can see if x tends to infinity, well, the numerator doesn't have an x anymore, so that's not concerned. That's just a constant. But the x is still here, right? And these expressions, obviously, those tend to infinity, right? So what you get here is 1 over infinity, so that tends to 0. So in some cases, you'll have to apply L'Hopital's rule more than once to get a result. What you'll usually see is that one of the expressions becomes simpler if you do that, at least one of the expressions. And if you do that and are not done after one application, it might be reasonable to try another time, and maybe more than just 1 or 2 times. All right, any questions about L'Hopital's rule before we go to the examples? So the point of these examples is, oh, there's a question, yep. Sure. So the question is it possible to start using L'Hopital's rule, maybe not get an immediate answer, but then have an expression that you know how to handle with a different strategy, and then change that strategy and compute the limit? Of course, that is totally fine, as long as you can prove the limit exists, right? So a limit that does not exist and does not tend to plus or minus infinity, we've seen examples for that. For example, a function that has a jump somewhere, right? And you have a limit from the left and a limit from the right, but they don't coincide, so the limit at that point just doesn't exist. That's an example for a limit that doesn't exist. Or also take the function 1 over x as you approach 0. One part tends to infinity, the other tends to minus infinity. Yeah, so those do go to plus minus infinity, one-sided, but the limit itself doesn't. That just doesn't exist. So the L'Hopital's rule also works for one-sided limits in the same way, yes. All right, again, let's see a couple examples. So basically the point of these examples is to show you not straightforward applications of L'Hopital's rule, right? If you have an expression that is not immediately in the form that it needs to be, it might still be possible to apply L'Hopital's rule if you know how to do it correctly. And here's some examples for certain types. One possible type is of this form. You have an expression that goes to infinity minus another expression that also happens to go to infinity. Right? Consider something like this here. In this example, x tends to 1 from above, so here we have a one-sided limit. And here, well, of course, you can just substitute 1 here. If you do that here, you get 0 from the positive side. So this expression goes to infinity. And here, this here, x minus 1 goes to 0. So e to the x minus 1 goes to 1. So this also goes to 0. And that means this expression also goes to infinity. There's something of the type infinity minus infinity. And one possible strategy to handle these is to try and apply L'Hopital's rule with a suitable reformulation. And that's exactly what we are trying to do here. Basically, the reformulation is pretty simple. You just reformulate that so that it all becomes one large fraction. And if you do that here, you'll find that now you're in a situation 0 over 0. And that is a situation where L'Hopital's rule might possibly be applied. So if we give that a try, what happens is we get this new expression over this new expression. And then if you try to substitute x, you'll find, again, that's a 0 over 0 situation. Yeah, so it hasn't become that much easier. But if you do one more iteration, then basically this minus 1 goes away, right? So that's what you want. If you do one more iteration, you'll end up with this expression over this expression, so it becomes a little simpler, not that much, but it's sufficient to make those zeros go away. And now, if we just substitute x, we get 1 here, we get 1 here, and here, 0 here. So we end up with 3 over 2. So the limit does exist, and it means the application of L'Hopital's rule was actually justified. Okay, so basically if you have an expression like this and don't see another way, try to put it all onto one large fraction and see if maybe L'Hopital can be helpful. Another pretty common type is this here. So you have not a fraction, but instead a product, a multiplication of two expressions. One goes to 0, one goes to infinity. Here's an example, right? X ln x, the x goes to 0 as x tends to 0. The ln goes to minus infinity. How can you compute the limit? One possible way is, instead of writing ln x times x, you write ln x divided by 1 divided by x, right? Same thing. but now we have a fraction. And in that fraction, this expression goes to minus infinity, and this goes to plus infinity. So now we are in that infinity over infinity situation that we need for L'Hopital's rule. And if we apply L'Hopital, you see, well, this of course gets a little more complex, but the important point is it makes the ln go away. Recall that last week we've discussed the derivative of the ln function, that is 1 over x. Right, so we're getting rid of the ln function, and now this is the limit that we can compute. Yeah, just reformulate that. That's very basic, and turns out that is 0. All right, so another situation where you can apply L'Hopital's rule if you just do the right reformulation. Keep that in mind. Similar ideas for the next two situations, basically. Let's say you have something with an exponential function of the type 0 to the power of 0. Right? Again, nothing that you can immediately see. So here's an example, x to the power of x to 0. This goes to 0, this goes to 0. So the question is, what will the limit be? In situations like this, it's usually a good idea to first reformulate that using the e to the ln trick, right? So instead of that, you write e to the ln of the expression, and then you can apply the rules for computing logarithms. So this here can be written here. Yeah, so ln of x to the power of x is x times ln x. That makes the expression look a little nicer. And if you remember what we did in b, we computed the limit of exactly that expression, x ln x. So we're again in that situation. That was 0. So e to the 0 is, of course, 1. Right, and similar situation here. That's not 0 to the power of 0, now it's infinity to the power of 0, so something like x to the power of 1 over x as x tends to infinity. So this goes to 0, this goes to infinity. Again, rewrite it in that way, e to the power of ln of the expression. Again, use the logarithm rules to rewrite it in that way. And then you have this limit here, ln x over x. And this goes to infinity, this goes to infinity. So for that limit, you can again apply L'Hopital's rule. And if you do that, you'll find that limit is 0. So e to the power of 0 is again 1, and here we have our limit. All right, and please note most of those limits that we've just seen here are pretty important, so e is pretty arbitrary, but here, that x ln x limit, you should keep that in mind. X to the power of x, that appears more randomly. But this one is important specifically because of a special situation. Note that something like n to the power of 1 over n, that's a special type of that. And that is just the nth root of n, right? So in particular, that sequence here tends to 1. All right, and finally, reversed situation, 0 to the power of infinity. Of course, again, same trick, right? You take this expression, you rewrite it as x to the power of ln of the expression, then you apply the logarithm rules to get that here. And then you have a limit that you can use. Well, you have to do a little more here. So 1 over x is x to the power of minus 1. And again, you can apply the logarithm rules. Pretty useful. Just writing that as a minus in front of this expression. And then we're back at x ln x, and we know that limit. All right. Yes? Sorry? Yep. This year? Well, if I have something like 0 to infinity, so that means this expression, the first part is going to 0, and that part here is going to infinity, right? So this part here kind of draws the whole thing towards 0, because 0 to something is basically 0, right? Well, this part here draws it to infinity, yeah, because something to large exponents will produce very large numbers, right? That goes to infinity. If we didn't have 0, but something like, I don't know, 2, 3, 4, something like that, right, we would get a very large number. So it's not immediately clear what happens. It's kind of the question is which of those two is faster. And of course, in this case, you'd easily see that this is very fast, right? Yeah, that's just produces very small numbers below 1 specifically, right? So you don't have that effect anymore. But that might not be immediately clear. Maybe the exam is too simple. All right, any more questions? Otherwise, maybe let's look at some more examples for L'Hopital's rule before we go on. First example is on the homework sheet, exercise 13.1. I've asked you to compute 3 limits using L'Hopital's rule here. And of course, I'm interested in your results. So I've set up tweetback quizzes for those. Let's take a look. Somehow tweetback is slow today. Let's see if it'll start anyway. Use the tweetback link already. Yep, so I started. So I have 3 quizzes. 1 for A, 1 for B, 1 for C. Let's see what results you got. So I'll give you 1 more minute to answer these 3 questions. And we take a look at the results. All right, let's take a look at your answers for A. Let's see. Well, I don't have a reliable connection today, once again. So maybe let me just tell you. So for 13.1a, about 2/3 of you voted for 2. And then we have about 20% saying 0. A couple other values, and about 11% say the limit doesn't even exist. So 2 is the right answer. Right? For A, 2 is the right answer. Maybe let's take a quick look at that. Doesn't seem as easy as I thought it should be. 31A. Right, so here we have the limit of ln x to the power of 6 plus 1 over ln x to the power of 3, and x tends to infinity. So as x tends to infinity, now we got it. As x tends to infinity, of course, these polynomials here go to infinity, and it also means the ln of that goes to infinity, right? So we are in the situation that we have two differentiable functions. We have an infinity over infinity type here. And that means we can give L'Hopital's rule a try. If I do that, I'll usually indicate that by writing this LH above the equation sign. I suggest you also find some kind of indication so that the correctors know what you are trying to do, just in case you get something wrong and it's not obvious. All right. So specifically, if you have limits that include the ln, you could get rid of that unpleasant function once you differentiate it. So usually L'Hopital's rule is a pretty good idea here. So in that case, if we differentiate the ln, you remember that the derivative of the ln is 1 over x, right? So in this case, we have to use chain rule. That means first we have 1 over the argument. So for the numerator, we get 1 over x to the power of 6 plus 1. And then we have to multiply with the derivative of the argument. So the derivative of x to the power of 6 plus 1 is 6x to the power of 5. And similarly for the denominator, 1 over x to the power of 3, and then we multiply by 3x squared. And I forgot the limit. Let's write that in front of that. And now, of course, we have a huge double fraction. Let's just simplify that a little before we go on. So what do we have here? In the numerator, we have 6x to the power of 5 and x to the power of 6 plus 1 in the denominator. And we multiply that. Let's see, this here goes in the numerator. So we have x to the power of 3, and we have 3x to the power of 2 in the denominator. Okay, that means a lot of that just cancels out. So in particular, we get rid of this 3 to the power of x squared. 6 over 3, that means we're left with 2 here. We have x to the 5 plus x to the times x to the third, so x to the power of 8 in total. And we cancel out a factor of x to the power of 2. That means we're left with x to the power of 6. And this x to the 6 plus 1 also stays. And now we have a situation that we know how to handle. It's polynomial over polynomial, basically. So we usually divide by the highest power. In that case, that is x to the power of 6. And that means we get 2 over 1 plus 1 over x to the power of 6. So obviously, Well, this 2 tends to 0. That means this tends to 1, this tends to 2, so we get 2. And obviously that is a finite value, so the limit exists. And that means L'Hopital's rule may be applied in the first place. Right? And here's an example where basically we switched from L'Hopital's to some more traditional method of computing the limit in the end. Question? So you're saying basically I mixed up the contents of f and g when I rearranged that huge double fraction, but that doesn't matter. So basically what I do is I apply L'Hopital's rule once, I get this expression, and now the question is, well, does this limit actually exist? And to find that out, I can just use traditional techniques, and that's just what I'm doing. And rearranging is one of those, right? I may do that freely. Of course, if I were to apply L'Hopital's rule once again here, then f and g would be completely different. But I could also do that. Then I would have to check again. Exactly, yeah? Of course, that would also be an option. Right? If you're here, of course, you can also use L'Hopital's rule to solve that one a couple of times, but you'll get there. All right, so that should settle A, hopefully. Any more questions about A? Otherwise, let's have a quick look at the others. B, so here's B. Most of you said the limit is 0. Let me maybe once again pull up B so that we know what you're talking about. So this here is B, x ln x. Well, if you paid attention before, you know that we have computed that limit already. So it doesn't make a lot of sense discussing that, I guess. So of course, those that said 0 are correct. So let's look at C right away. And C is maybe a little more interesting. So C is this function that involves the sign and it involves the ln of some absolute value. So that looks suspicious. And I need to get tweet back to switch, but I can't. And in that case, most of you voted for the limit doesn't exist, about 42%, 43%. About 37% said the limit is 0. Oh, here you have it. And then there's a couple of votes for 1, 2, -1, -2, things like that. So maybe let's see what we can say about that, actually. C. Let me write down the expression once again. We want the limit as x tends to 1 of the sine of pi x times ln of the absolute value of x minus 1. All right, so the problem in this situation that most of you have recognized is, of course, this absolute value here, right? So you have the ln at an absolute value. We may have problems with differentiability in that situation. But remember that I've told you that L'Hopital's rule also works for one-sided limits, and of course then it's sufficient to have one-sided differentiability. And that means we can still give that a try. If we restrict ourselves to one-sided limits, get rid of the absolute value, and then compute the one-sided limits, if that works. And we just have to compare those. And maybe the limit does indeed exist if those would be equal. Right? So we can use L'Hopital's not for the global limit immediately, but we could use it for the one-sided limits and see if that gives us a usable result. But before we do that, actually let's have a look at that fraction here. So what we have here is the sign of pi x, if you remember what the sign looks like. Basically, sign function looks like this, and this is pi as x tends to 1. Of course, sine of pi x tends to sine of pi, so that goes to 0. right? And then we have this ln. As x tends to 1, x minus 1 tends to 0. So the ln, of course, tends to minus infinity. So we have a 0 times minus infinity situation, and you remember how to resolve that if we want to apply L'Hopital's rule. Basically, the first idea is to rewrite that as ln of x minus 1, absolute value, over 1 over sine of pi x. Right? Of course, that complicates things a little, but now we have a situation that is something like minus infinity over infinity. Yeah, plus or minus. Doesn't matter much. Okay, and now to resolve that situation, of course, we could use L'Hopital's rule if you could make this at least one-sided differentiable. And so we'll take a look at the one-sided limits. So let's first try to compute the limit as x tends to 1 from above. So in particular, that means x minus 1 is positive. Right? X is greater than 1. Okay, so that means we have to compute this limit here. Let me just write that down once again. Once over the sine of pi x. And now we can get rid of this absolute value because we know the argument of the ln is positive. Right? So this is ln of x minus 1 over 1 over sine pi x. And now we are again in this infinity over infinity situation, right? That means we can try to apply L'Hopital's rule. Both are at least one-sided differentiable. Right, so what we get here is 1 over x minus 1 for the ln. And for the sine, that is a little more complicated. There we have, let's see, 1 over minus sine of pi x squared times cosine of pi x times pi. Right, so repeated application of the chain rule. All right, let's rewrite that to make it a little simpler, hopefully. So basically we have the sine in the numerator, right? Sine pi x squared. And in the denominator we have all the rest, right? So this is, I also put the minus sign in here, minus x minus 1 times pi times cosine of pi x. All right, so did that help? Let's see. Well, this sign obviously still tends to 0. What about the cosine? Maybe let's draw that as well. Cosine, that looks approximately like this. So that's the cosine, that's the sine. So in particular, the cosine of pi is what we want. Here the value should be minus 1. Right? So this here tends to minus 1. This here tends to 0. And of course, pi is just pi. So again, we have a situation that we can't immediately resolve. It's something like 0 divided by 0 right now. And that means we are again in a situation where we could apply L'Hopital's rule, if the limit exists in the end. We'll see about that. So let's give that a try. All right. Differentiating that here, again, we apply chain rule. That means we get 2 times the sine of pi x times, now the derivative of the sine is the cosine, so cosine pi x. And now we need to differentiate the argument of the cosine. So that's pi x differentiated, that's pi. All right. For the denominator, well, let's see, what do we have here? Well, this is a product of these two, basically, so we need to use product rule. Let's start by differentiating this expression here first. We just keep the minus somewhere in front of that. Differentiating x minus 1 just yields a 1, right? Let's maybe take the pi out to make things a little easier. Just a second. So like that. So differentiating x minus 1 yields a 1. So we have 1 times cosine pi x. And then we differentiate this expression and we keep x minus 1. So plus x minus 1 times, and now differentiating the cosine. The derivative of the cosine is the negative sine. So minus sine pi x. And again, we need to differentiate the argument, chain rule, so times pi. All right, that should be it, hopefully. And now what do we have? Well, let's see. Sine pi x, again, that goes to 0. The cosine goes to minus 1. So basically this whole expression goes to 0. For the denominator, we have a minus 1 here. This goes to 0. This goes to 0. So we have minus 1 times minus pi. So this goes towards plus pi. And now we finally have a situation where we can just substitute the values and get our result. So that's 0 over pi, or just 0. And remember, the limit exists. So L'Hopital's rule may actually be applied. Right, so this gives us one part of the answer. At least we have a one-sided limit. And now we can try the same thing for the other part, analogously. So now we would try to find the limit as x goes to 1 from below. And let me just show you the start here. So again, we have this formulation. As x goes to 1 from below, we know that x minus 1 is less than 0, sorry. That means the absolute value can be expressed by reformulating that as ln of minus x minus 1. Right, or simply ln of 1 minus x. And then we're again in the same situation. We have two functions that are both at least one-sided differentiable at that point, so we can try to use L'Hopital's rule and basically go through much of the same steps that we've just seen. What will happen? I'll spare you all the details. Basically the same calculation that we've just seen above. What we get is a limit of 0 over minus pi. So again, 0. So that means both two-sided limits exist. and have the same value. So the limit exists, and what we get is the limit of, what was the original formulation here? Sine pi x times ln absolute value of x minus 1 as x tends to 1 exists and has a value of 0. So those who said 0 were actually right this time. Right, so we have to do a couple of involved computations. Make sure to not get the derivatives wrong at any point. But otherwise, it should be pretty straightforward. Basically a matter of concentration. Any questions about this? Yes. This step here? Yeah. So you want it reversed, basically. You can give that a try. The downside, of course, is, I mean, we now know that the limit will be 0, right? So if you reverse it, what you'll get is a limit of infinity. That doesn't exist. So you can't apply L'Hopital's rule. So in this case, you probably shouldn't interchange it. But of course, we only know that in the end. Right? You could give it a try. I mean, I did it because I knew what was happening, of course. I could also have tried it the other way and then found out that doesn't work. So let's reverse the situation, try again. But good question. Any other questions about this? Yes. So basically your argument is the situations for the two-sided limits, those are kind of symmetric, apart from the sign. Yes, of course you could argue that. Yeah, it's exactly what would happen here. And basically you can see that here already. It still makes sense to solve it again, just in case you made a mistake and maybe you discover it that way, I'd say. But yeah, you could shortcut that, pretty much as I did. Other questions? Otherwise, I think that covers the homework sheet, right? Well, the one question next is about Taylor. So I'd first have to discuss Taylor. Maybe let's take a look at some more L'Hopital's limits before we do that. I do have two exam problems that you wanted to see anyway, so maybe let's tackle those right now. The first one is from the exam 2019-1, problem 8a. Let me quickly write that down if I can hopefully find it. That should be it. So here I'm asking you to compute the limit as x tends to 0 from above of x squared cosine x divided by the square root of sine x. Okay, so that's the exam problem. Let's see if you can solve that one. Should be worth about 3 points, 4 or 3 points. So 5 minutes should be more than sufficient. So for those who haven't seen it yet, I have set up a tweetback quiz asking for your answer to that question. So once you're done, please submit your result there. So quick show of hands, who's done with the problem? Who would like some more time? Give you a couple minutes more. All right, I think that should be sufficient. So let's take a quick look at your results. I'll give you 30 more seconds to submit your answer. All right, so most of you voted in favor of 0, 77% almost. About 13% said the limit doesn't exist. No, yeah, you can see. Interesting, you have different numbers. Okay, yeah, but the tendency is about the same. So most of you said the number's 0. So let's have a look at that. As you have probably guessed, this will be an example for L'Hopital's rule. So if we have x tending to 0, well, what do we get here? The cosine of 0 is 1, so that tends to 1. X squared, of course, tends to 0. The sine tends to 0, and that means the square root of the sine also tends to 0, right? So we get 0, and of course 0 times 1 also goes to 0, okay? So that means we have a 0 over 0 situation. And of course all those functions are at least one-sided differentiable. So we can give L'Hopital's rule a try here. That's what we're going to do. So this means that's the same as the limit as x tends to 0 from above. Let's differentiate that. X squared times cosine x. We just apply product rule for that. We start by differentiating x squared, so that's 2x times cosine x. Plus, and then we'll differentiate the cosine. So we copy the x squared, and the derivative of the cosine is the negative sign. So that's times minus sine of x, right? For the denominator, we have the square root of sine x. You'll hopefully remember the derivative of the square root function. Just in case you don't, that was 1 over 2 times the square root. So we use chain rule, of course, and we get 1 over 2 times the square root of sine x times, and now we need to differentiate the sine of x, and the derivative of that is the cosine. All right, so that's what we have. Let's try to simplify that. What do we get? Well, this square root expression that goes in the numerator, so we have 2 times the square root of sine x here. Then we only have this cosine of x in the denominator. And here we also get, let's see, what do we have? 2x cosine x, well, not a lot we could simplify there, minus x squared sine x. All right, so let's take a look at that. Again, the sine here goes to 0. The cosine goes to 1. The x goes to 0. This goes to 0, and this goes to 0. So the numerator will go to 0. The denominator, which is just the cosine of x, that goes to 1. So now we have an expression of the form 0 over 1, and obviously we can just substitute our value of x in there and get the desired result, which is 0. All right, so those of you who said 0 were right. Any questions about this one? So I'd say, of course, you have to figure out that you need to use L'Hopital's rule. That was that obvious in the exam, maybe. We didn't just discuss it before. Once you get that, of course, you again have to get the derivatives right. That should be a pretty straightforward application of the rules here. It's not that nice, but I think you can handle that. And then it's just substituting x into the expression and immediately get the right result. As I mentioned, you should, of course, mention at this point the limit exists, and therefore L'Hopital's rule may be applied. Please don't forget that in the exam. All right. I think we have time for one more exam question. You also requested 2019-2. Problem number 7. Let me write that down. Where do I have that? Right here. All right, so the problem statement is compute the following limit for x tends to infinity of x ln x squared plus 1 over the square root of x to the power of 3. So again, I'll give you a couple of minutes to figure that one out. And as usual, for those who are done, I managed to start on the tweetback quiz. Quick show of hands. Who's done already? Who wants some more time? Maybe just give it 2 more minutes. All right, time's up. So maybe TweetBack will show the results in a minute. In the meantime, let me say that we seem to have a tie. About 47% voted for 0, about 47% voted for the limit doesn't exist, and then a few votes for 1 and 3. All right, so let's try to figure that one out. If you look at that limit, it's hopefully easy to see that this expression inside of the ln, that tends to infinity. So of course the ln will go to infinity, x will go to infinity, so the numerator goes to infinity. And the same is true for the denominator, right? So it's a infinity over infinity situation. Both terms are obviously differentiable, so we can try to apply L'Hopital's rule. However, there's one catch that you should pay attention to here. And that is, before you apply L'Hopital's rule, it might make sense to take a look and see if you can simplify something. And that is, of course, the case here. If you look at this and this expression, you notice x goes to infinity, so in particular x is positive, and that means the square root of x to the power of 3 is the same thing as x times the square root of x. So if we use that, we will be able to just cancel out one of these x terms here. And if we want to differentiate later, that will make our life easier. So let's do that first. Right, so that's the limit as x tends to infinity. Let me just write that down once again. Over x times square root of x. And then let's simplify that. And we have ln x squared plus 1 over the square root of x. And of course, still, this tends to infinity. This tends to infinity. So we still have an infinity, oops, not over 8, of course, infinity over infinity situation. And we can now apply L'Hopital's rule. All right, so let's do that. And what we get is the limit. Let's see. Differentiating the ln will give us 1 over x squared plus 1. And then we need to multiply by the derivative of this argument, x squared plus 1, that's 2x. And for the square root, we just get 1 over the square root of x, 1 over 2 times the square root of x. All right. Again, let's write this on one fraction to simplify things a little. So what we get is, let's see, 4 times x the square root of x, right? So that is this expression and this one here. And then we have this expression in the denominator, so over x squared plus 1. And this is again a type of limit that you should be familiar with. Basically a polynomial. The only exception of the square root here, but can treat it in very much the same way. What we do is we divide by the highest power of x. We have an x squared here, and here we have an x times square root. So square root is the same as x to the power of 1/2. So that's basically x to the power of 1.5. So the highest power is x squared. And that means if we divide everything by x squared, we get 4 over the square root of x and 1 plus 1 over x squared. Right, and now this here tends to 0. This here tends to 0, so the numerator tends to 0, the denominator tends to 1, and that means we can simply use these values here, and we get 0 over 1, which is 0. And again, the limit exists, so that means L'Hopital's rule may be applied. All right, any questions on this one? And there's no questions on the tweetback either, apart from those that I want to discuss tomorrow anyway. So I guess that's a good point to stop for today. Tomorrow we'll talk about Taylor polynomials and Taylor series as a way of approximating functions. So have a nice day, and I'll see you tomorrow.